All right, ladies and gentlemen, it gives me more than tremendous pleasure to introduce the next speaker. Kohta Ueno has an undergraduate degree from MIT and a master's degree from the University of Waterloo, and he's one of the finest minds in building science around. He has weird habits. He plays the piano exceptionally well, and he builds furniture. You know, from somebody from MIT, that's pretty impressive. You know? So, a practical skill. I mean, from MIT, oh.
Joe, I know practical things despite my education, not because of it.
He's going to talk about multifamily buildings, and to say that we've been having or seeing problems with them is an understatement. Kohta is probably the foremost expert in the issues. So, and is that a Spanish name? Bueno? I think have I crossed the line with that yet? I'm not sure whether you're allowed to make jokes. But but let me explain. I'm a cancel check. Take it away, Kohta.
Thank you, Joe. Thanks very much for being here. So before I get started on this material, I'd just like to take one of those moments to, a little bit of origin story and basically give a massive thank you to all of the mentors out there. There are way too many of them here in this room to name, but I'm just going to talk about a few of them who are really formative in my origin story, if you will. So rewind back to 1998. I was a young engineer with construction experience, trying to figure out which direction my career was going to go in, and I was watching an episode of Nova on PBS. And this gent here, Joe Stiebrick, was speaking as one of the talking heads, "Can buildings make you sick?" And it's like, that sounds like a kind of interesting field. Cold call them, Betsy answered the phone, and I was incredibly, incredibly lucky that they were looking and welcoming a new entry-level person at that time. I consider that the massive act of serendipity in my life and my career to have actually gotten to work for him in this capacity. So, he's been, basically the prime mentor in my working career, incredibly generous with his time. Both Joe and Betsy running an incredible company as well, for sure. Then, after, fast forward to 2003, working for Joe, John Straub was consulting for us on some monitoring projects, said, when are you coming up to Waterloo to do your master's degree with me? It's like, that sounds pretty interesting. And basically, it was the perfect finishing school for building science, being able to walk into saying, I call BS on your radiant barrier theory over here. T to the fourth minus T to the fourth, it's not happening here. Come on. So he is, probably one of the top building science minds and educators of the generation. Once again, incredibly lucky to have worked with him, to have worked with all of my colleagues who are mostly now at RDH, basically a fantastic group of people. And third, Andy asked, basically the reason why I know, as much about moisture, big building mechanicals, HVAC, moisture control, Andy, Lou Harriman, those are some of my formative folks. I am all in my debt to all of you as well as all the other mentors. So, however, working with these guys over a whole bunch of time, I've gotten a whole bunch of awesome candid shots of them. So this is Joe Stiebrick back when he was doing real work, digging a hole in the green roof and filling it with water to look for water leakage. And in the meanwhile, the lawyer is looking out from the window going like, what the heck is this guy doing? And so back when he was doing real work, but Joe, I assume you're not, you have no desire to do that anymore, right? Yeah, and this is John Straub. In case you can't tell quite what's going on, John Straub is adjusting a weather station while standing on top of a sawhorse on top of a roof in New Zealand. You can see at least he's smart enough to have one of his grad students hang onto his belt, but you kind of imagine the dialogue of like, John, when are you signing off on chapter 8 of the thesis? And lastly, Andy, he still comes down into the crawl spaces with all of us to check out the ductwork. No, he is not taking a nap here. He is actually shimmying underneath the ductwork. Although, I had a discussion with a kid that I know, and he said, and saw this picture, it said like, Santa's coming into the house the wrong way. But anyway, so what I'm going to be talking about today is multifamily summertime humidity problems. And I want to first acknowledge full well that there are probably a whole bunch of this audience who can give this talk at least as well as I can. And there are other ones who they doesn't overlap with your day-to-day work, and other ones where your experience is, I own an air conditioner, so there'll be a wide variety of audiences. Apologies to those who I'm going over too much basic stuff, but I'm trying to keep stuff as accessible, and if I gloss over subjects as well, my apologies too. So, we've been seeing a raft of problems of multifamily high summertime humidity problems. Typically, they're new construction, and the problems manifest as condensation, staining, mold on the registers, things along those lines. Moisture problems all over the place, and even worse, inside the unit itself, staining on furnishings, furniture, the tenants complaining that they have to take their shoes that are covered with mold out for cleaning. The ownership is getting really tired of dealing with that. And in addition, a lot of these cases have ductwork inside the floor truss between the conditioned spaces, and they're actually having condensation and dripping on those surfaces. All this matches up with what the occupants are complaining about, saying, yeah, sure, it gets cool, but it's really clammy and nasty inside here. It is not pleasant at all. And, they add, the ownership team typically goes ahead, here are the problem units, we'll throw in a dehumidifier, solves the problem for a while, but it gets expensive, dropping in these units, pouring the condensate out of the dehumidifiers. It's basically a Band-Aid solution, and the owners are looking for something that will take basically provide a longer-term solution to these problems. So just a couple of candid shots of what the problems are. Here's one of the projects that's in Philly. Brand new multifamily building. They actually had to demo the ceiling because it was so wrecked by water pouring through it. This is a truss that is between two conditioned floors. You can see that sweating, that line of condensation dripping down onto the ceiling, and even that HVAC cabinet that's inside the HVAC closet, you can kind of wipe your hand over it and wipe away a line of sweat on that. Going down to Savannah, Georgia, similar kind of thing, brand new multifamily, and all this crap on the ceiling of nasty moisture stains, condensation next to the ductwork grills, mold growing on furnishings, sweating inside the microwave and the cabinet. It even comes up to Long Island, Climate Zone 4, similar kind of construction, similar kind of problems. That top left corner picture is looking upward inside the HVAC closet, and you can see all the spotting of mold that's growing up in that ceiling. Once again, crap growing on furniture. Going inside the return, you see that basically there's spotting all over that. Baltimore, same kind of thing. This is a weird one. I only got to investigate it over the winter, so basically looking for clues in the ashes. And you could see that basically they had to rip down the ceiling in the corridor where that HVAC duct comes out, obvious signs that it's been dripping water for a long time. So Where are these things happening? Just most of them that I've been investigating personally have been climate zone 4, basically over on the East Coast, ranging from Long Island down to Virginia. So if there's one key takeaway from this map, don't build stuff in New Jersey and you might be safer. I'm going down to climate zones 2 and 3. Yeah, there's definitely other things. I'm not saying I have a representative sample. There's probably some kind of sampling bias in terms of who calls me. And typically, like I said, mid-rise multifamily, although also some of these are townhomes, assisted living facilities, hotels. Similar type of things, though, where they are high occupancy, lots of little units, boxes with people living in them. And typically either new construction or recent renovations. Anecdotally, a lot of the things that I hear on that first call, talking to the client or the property manager is, it's an Energy Star project. I've been having problems with these, or this didn't happen on the last one. What's going on here? All of these, pieces will be put together. So just a brief outline of the topics that we're going to be covering. Indoor and outdoors as sources of moisture. Whole session on cooling sizing and basically matching up cooling equipment to the loads of these multifamily buildings, the individual units. Mechanical ventilation systems, how they're put together and how various ways that they work. Air leakage and humidity. Mechanical systems and dehumidification. What makes them dehumidify? What makes them not dehumidify? And if they don't dehumidify, what options are on the table for dehumidification systems? And we're going to wind that up with a bunch of case studies, just little anecdotes from a lot of these investigations that we looked at. So, starting off talking about indoor and outdoor moisture. So, I assume all of us have seen the Sterling chart. My esteemed Dr. Bales has posted it on his blog, basically just showing the various levels of risk at various humidity levels. Obviously, down at the low end, sorry. Oh, it was me or the mic? There you go. Oh, just drop it. There you go. Thanks so much. Check. Oh, check. Okay, we're back up and running. Okay, Sterling chart. Basically, horizontal axis is relative humidity, showing the risk of various types of detrimental things over various humidity ranges. And basically, what Dr. Stephanie Taylor over there can basically spend an entire day discussing the entire microbial side of things and basically do a master class, which she has done in previous summer camps. But the part of the chart that I'm talking about over here is the high end. Basically, a lot of the problems, 60% or higher, that's the range where problems start to happen. So higher RHs, mold risks, and becomes a visible problem or symptom. In reality, 80% and higher out to the condensation range is the really risky range for mold, but 60% is a great starting point for discussion of keep stuff under 60% and you're going to be safe for the most part. So let's talk a little bit about indoor and outdoor dew point. So for those of you not familiar with the psychrometric chart, table of moisture properties in air, horizontal axis, temperature, vertical axis, absolute moisture content in the air. There are all these different ways that we can measure moisture in the air, state that absolute moisture content. There's, for instance, grains per pound, basically how much moisture is in a pound of dry air, which is maybe useful if you're trying to figure out how much moisture you're going to wring out with a dehumidifier, but does not give you much for intuitive understanding. You can also state it in terms of vapor pressure. If you are a roofing consultant like Matt Dupuis and you want to talk about blistering in your roof assembly, sure, that's that's the metric to use. Or if you want to show up, demonstrate your dominance as the alpha geek in a building science table, sure, you can start talking about vapor pressure. But if you want to be understood by normal people, talking about dew point is way more reasonable, I would argue, for a couple of reasons. One is that there's a physical phenomenon that you can relate it to. Air that is at a certain dew point will start to condense out of the air when it hits a surface at that temperature. If you're in muggy Florida and you have 70 plus 80 degree dew point, that makes perfect sense if you walk outside and your glasses fog over from when you walk out of the air-conditioned building, because that's the temperature of your glasses. And also it states a risk. If I am dealing with 70 degree dew point air, if it hits 70 degree dew points, 70 degree surfaces inside, yep, that's when the risks start to happen. The last reason I'm going to push for thinking in dew point is that there's a degree of intuition that you can have just by walking around and listening to the weather forecast. A 50 degree dew point, that's beautiful California weather, or the great weather this week that Joe ordered for us at summer camp here. You walk outside, it's not too wet, but you can moisture evaporates off of you quite nicely. 60 degree dew point, that's when you start to feel, yeah, it's getting kind of humid, I'm kind of noticing it. 70 degree dew point is pretty disgusting peaks of New England summer kind of thing. And 80 degree dew points is pretty much, bad, the depths of the worst of wet Florida. Or, even higher than that, I think you have to go to Guam to get dew points that high. Guidance from ASHRAE is in any air-conditioned building, you want to keep your interior dew point below 60 degrees dew point Fahrenheit. A useful tool if you are not enough of a nerd like Mark Rosenbaum or Henry Gifford to walk around with a psychrometric chart t-shirt is just go ahead and download this smartphone app. It's a useful thing if you actually have to calculate dew point from temperature and humidity or some other things. I actually use it all the time to figure out if it's time to open up the windows at home. Yep, that level of geekery. Okay. Moving to what are the actual seasonal behaviors of temperature and dew point. This is just a boring plot of outdoor temperature in orange, showing wintertime, summertime, wintertime, summertime, basically getting down into the single digits over the winter and up into the 90s over the summer. So that is the outdoor temperature. We change to what is the dew point during those times, and it follows, of course, the same pattern. Low dew points, low air moisture content in winter, high air moisture content in summer. And if we want to relate that to, say, interior conditions, that's, for instance, 70 degrees. That light blue line is 70 degrees, 60% RH, which is basically the upper limit of what I would probably want to run things at on the inside, or a decent upper limit target. And closer to comfort, 70 degrees, 50%. There's a wide range here, but the takeaway from this, obviously, is that over the summer, outdoor moisture levels are much higher than we want to have on the inside for comfort and to avoid problems. So, I'm dealing with some of these problems, and once in a while, the owner or some contractor says, you're building these new Energy Star buildings too tight, and your moisture is trapped inside. That is true for a winter time problem. The outdoor dew point is incredibly low and dry in the winter. Therefore, if we're keeping outside air out, that means that yes, we would be trapping moisture. However, in the summertime, that is actually the opposite problem. So, just to put on my science fiction nerd hat, I know there are lots of problems with the Star Wars trilogy, but there's this one moment in one of the movies where Rey is talking to Luke Skywalker and Luke is quizzing her, saying, what is the Force? And she says, it lets Jedi control minds and lift rocks. And Luke responds, amazing. Every word you said was wrong. And that's pretty much my reaction to when they say, you're building too tight. Obviously, summertime humidity problems are due to untreated outside air, unless there's a massive interior humidity source, a grow-op, a bakery, something like that. It's all about ventilation or over-ventilation, uncontrolled air leakage from outside, and poor dehumidification dehumidification. Basically, a combination of these factors is typically what I am seeing in all of these problems. Okay, pause for questions so far. Anything? Just keep on blasting through? Okay. Okay, so we're going to talk a little bit about cooling sizing and loads and the building enclosure. Like I said, there are probably a dozen people, 30 people in this room who could teach this session at least as well as I can, but bear with me. So, cooling in the summertime is the only mechanism of dehumidification typically available. And the cooling system is controlled, obviously, by temperature, not by humidity. There are rare exceptions, but that is the typical case. So the way that I always describe it is that we are incidentally dehumidifying when the air conditioner runs based on the temperature controls. So what does that mean in reality? If Armin Rudd is in the room, I'm not sure, but he spearheaded this research back in the early 2000s looking at some of our Building America projects. But basically, we were hired by DOE to work with production builders looking at their houses. This was down in Houston, working with a production builder, and basically we tried to get them to improve their construction in a cost-neutral manner. So we basically took some of their existing production and bumped up their efficiency levels. Brought their ductwork from up in the attic to inside, and changed their glazing from single glazing to double low E. Kind of shocking that folks were still building with single, but that's Texas for you. Upgraded insulation levels and high efficiency mechanicals, improving air tightness. So if we look at those last two bars in the graph, what we're comparing here is their original construction, standard reference, to that improved house. And we were measuring temperature and humidity inside all of these houses. And what we found is the number of hours that went over 60% humidity, that danger mark that we talked about, went from 5% of the hours to over 25%. So basically, was going on is we improve the shell, we improve the enclosure, less air conditioner runtime, therefore less incidental dehumidification. And the worst problems were typically occurring during the swing seasons, rainy days, high dew point, high humidity outside, not much call for cooling, and the whole thing just basically accumulates moisture at that point. So what kind of equipment are we typically, by the way, is this working still? Okay, still good? Okay. What are the typical mechanical systems we're seeing in these multifamily buildings? Typically, it's an air handler, a furnace, or a heat pump sitting inside an interior mechanical closet. And their ductwork is located up in the ceiling above the unit, above the, basically in the ceiling plenum assembly. And it's, because this is new construction, often Energy Star, it is typically higher efficiency equipment. Basically, as you can see, the roof is covered with all these individual condensers just lined up in rows, one for every single unit. So when you calculate the load on a multifamily unit, you have to think about it in terms of what loads are actually being seen here. And it's going to vary depending on construction, environment, as well as are we talking about something that just has one wall to the outside in the middle of the cube, or a corner unit, or with two sides, or a roof unit. All of these are going to be things that will affect what the design loads on the hottest day that you would need to size your equipment for. So just as an example, the Philadelphia project that I looked at, I ran the calculations, ran the manual J sizing, ranged from maybe 7,000 to 9,000 BTUs per hour for one of these units, depending on whether it's middle or corner or roof. And, of course, they all have the smallest commodity unit available. Basically a 1.5 ton, 18,000 BTU per hour unit that's basically oversized by a factor of 2 to 3 already on the hottest 35 hours of the year. So basically oversized by a factor of 3 on the hottest couple of days. And after that, even more massively oversized. And this is not restricted just to attached multifamily, high-rise, mid-rise buildings. I looked at a townhome set of designs. These were, both townhomes and over-under stacked units, one on the first floor, one on the second floor. 1,000 to 1,300 square feet. These were sized at about 2 tons per unit. Doesn't sound too terrible. And then so basically they gave me a set of the load calculations, looked at them, looked a little bit closer and said, well, yeah, 2 tons kind of matches up with those loads, and then looked a little bit closer. I don't know if you can quite read those gray bar, but the gray one is basically a full, almost a ton, accounting for interior loads, interior equipment, plus lighting on top of that. This, their manual J literally says arbitrary safety factors are indefensible in black and white in the document. The lighting load, you're supposed to add lighting load if you're doing a retail store and adding a bajillion halogens to light up your stuff, not in a normal residence. And the amount of equipment that they're talking about here is kind of, in their equipment load is ridiculous. Also, this is recent enough that everybody is installing more efficient lighting. This load assumed 1,000 watts in 1,000 square feet for the lighting load, which is absolutely ridiculous. Like, how would you manage to even do that if you were lighting your house with LEDs, for instance? You basically have to put on sunglasses when you woke up. So if you actually bring the loads down to a more reasonable level, we're talking once again about under a ton for each of these 1,000 square foot units. The loads are not there. This is going to be, once again, oversized by a factor of 2. So, once again, talking a little bit more about basics. Sensible and latent loads. So, the sensible load is the name given for the temperature-based load. The air conditioner turning your air from 70 degrees to 50 degrees to cool down your unit. The latent load is the dehumidification or the moisture load. The ratio of the two of them together gives you what's called the sensible heat ratio. Basically, if it's 70% sensible, temperature-based, 30% moisture, you have an SHR, sensible heat ratio, of 0.7. Mechanical equipment has a semi-fixed, is how I put it, sensible heat ratio. It'll probably provide dehumidification down to a certain point, but not beyond that. But also, if you feed it really dry air, some of that unused latent load will probably get converted back into sensible based on talking with John Proctor. But basically, there are lower limits to what you can achieve for dehumidification. The building also has a sensible heat ratio. It's the balance between what's coming through the shell, how much are people using toasters versus how much moisture are we dragging in by ventilation, and how much are people breathing. So a lot of these, and like we said, sensible load goes down, the latent load typically stays completely the same. People are cooking about as much, we need the same amount of ventilation, so once again, we're dealing with a mismatch between the sensible latent load that can be provided by equipment versus what the actual load is in the building itself. So pulling out a chestnut from ACA Manual J, and this is from decades ago. This is not even with the most current equipment. This is showing how dehumidification works over time when you turn on the air conditioner. So horizontal axis is minutes since you turned it on. Vertical axis is the mix of sensible versus latent. Temperature versus moisture. And you can see when you first turn on the cooling system, you get all sensible. The coil is not really that cold yet. You're not condensing out any moisture. You give it a couple of minutes to run, maybe like 5 minutes or so. Then we're getting down to 30% moisture, 70% sensible, that kind of thing. So the older equipment, you can see, basically after about 5-6 minutes, it gets down to 0.7 sensible heat ratio, and you're pretty much good from that point, and it'll basically stay there. In contrast, more modern, more efficient, higher SEER equipment is going to be worse at dehumidifying. How do you get better efficiency in this equipment? You make your coil larger, give it more surface area to blow through, and therefore you're doing less force with the fan to try to move that air through. The problem is same number of BTUs over a larger area means warmer coil, means less dehumidification results. And also, on top of this, all that stuff we were talking about equipment being oversized by a factor of 2 to 3 on a 95-degree day, it means this thing barely runs a couple of minutes and then shuts off. So it's barely dehumidifying at all. Okay, another pause for questions as we're going. I'll repeat the question. Don't worry, Andy. Anthony, sorry. The question was, if I'm running a mini split heat pump, does it make more sense to run it at low speed so it runs more? That's the direction we're going, but there's a whole section to talk about this, Steven. So we'll get to that. Luby, what's up? Okay, so Luby said what's going to happen when the code calls out for moving ductwork from the attic into the house? What is that going to mean for dehumidification? Basically, everything that we were talking about in Houston. You drive down the loads, air conditioner is going to run less, humidity problems are going to get worse. Am I going to say where we're going to have problems? No, but I don't know exactly where that happens, but the bottom line is the southern problems are going to continue to creep their way north the way that Formosan termites are. The way to think about it, in dehumidification, there's a concept known as reheat. You basically blow super cold, super dehumidified air, and then you reheat it, you heat it back up to basically make it more comfortable to not freeze out your occupants. So you can think about single glazed windows and attic ductwork as being a reheat system that you've built in accidentally, of basically dumping heat into your house, and we're getting rid of that, and therefore we're getting rid of that built-in dehumidification system. Yes, sir?
Yeah, but my HVAC contractor told me that the turn-down ratio is really big, so therefore oversizing doesn't matter.
Oversizing doesn't matter because of the turn-down ratio. Yep, we're going to get to that for sure. Okay, moving on. Okay, multifamily ventilation systems and multifamily buildings. There are a couple of different flavors of what you can do. So exhaust-only ventilation, the favorite choice of cheap developers. You can basically take a crappy bathroom exhaust fan, turn it on, run 24/7, and you now have a ventilation system. As a result, what does it do? You can see by the pink arrows that it depressurizes the building. You are sending air out, and it is drawing in outside air through the leaks and cracks through the shell. Basically, wherever the leaks and cracks occur, that is where you will get outside air. It is drawing that air from an unknown source, wherever your holes are. It could be drawing it from the garage. It can be filtering it through the mouse crack in your wall. It could be filtering it through whatever is inside, dead bodies are inside your wall. And in reality, in a multifamily building, you add up all of those little exhaust fans, all of them still are running. You throw a flow meter on them. Each of them are sucking typically their 50, 70 CFM, especially if they're a good Panasonic. So basically all of that air is being made up from somewhere. It ends up being wherever in the building the largest leaks are. So adjacent units filtering through from others, adjacent unit with the window open, corridors, shafts, elevator tops, whichever ends up being the big holes. Yeah. The opposite of that is supply-only ventilation. We are grabbing air from outside, injecting it inside, and we induce exfiltration. Air leaks from inside outward through the shell. We are at least drawing the air from a known source, so we have the opportunity to filter it. Whoa. But the problem is we're drawing outside air and sending it inside. So preconditioning it, mixing it, something to avoid dumping 0-degree air in winter and steaming hot doo-doo air in summer. The most elegant version of doing a supply ventilation system, I would say, is probably central fan integrated ventilation. Once again, credit to Armin Rudd. Basically, it's an outside air duct connected to the return side of the air handler with a motorized damper so that whenever the air handler runs and the damper is programmed to be open, we're pulling in outside air, mixing it with the rest of the building, with the rest of the air circulating through the air handler and distributing it throughout the building. Of course, with high-performance buildings, the direction that a lot of them are going are heat recovery ventilators, energy recovery ventilators. Pressure neutral for the building, where we are simultaneously exhausting and supplying air to the building and exchanging heat in the process. Once again, we're drawing the air from a known source, and it works perfectly well with tighter construction, does not rely on figuring out where the holes are. Of course, there's the energy benefit from the heat recovery, and of course, it is the highest cost option. So, central units or individual ventilation systems. This has long been a debate within the whole multifamily industry. Joe Stiebrick is a very strong proponent of compartmentalizing the heck out of every single unit. You basically want each apartment unit to be its own airtight box floating in the sky, not connected to anything adjacent to it, not sucking in the fish odors from the first floor, secondhand smoke, whatever crap is coming through. That lends itself very well to individual ventilation systems located within each unit. Basically, each box in the sky has its own little ventilation system sticking out through the wall. The pushback that we get from industry is that, somebody, maintenance guy, has to go to every single one of these HRVs or ERVs, make sure it's running, swap the filter. They're going to have problems getting that access, making sure they're still working. That's entirely a fair problem. The problems with the central type of systems is that you're basically sinking shafts running from the rooftop to every single unit, and you have to do a whole lot in terms of compartmentalization, fire smoke dampers, balancing, all of those problems. Also, in terms of cost, I saw a study by Stephen Winter where they had two side-by-side projects in Brooklyn, central rooftop ERVs versus individual units. Their numbers were individual units were an order of magnitude cheaper. That's the number that they gave me, but it was kind of shocking to me. A decent compromise that I've seen some folks implement is a floor-by-floor system. You centralize to a mechanical unit on each floor, a mechanical closet, run the ductwork above the ceiling to individual units, but then you're no longer running fire-rated shafts up and down the building, losing that square footage. That, to me, that's a pretty reasonable compromise. Options that are out there. Here's an example of doing a semi-balanced system of central fan integrated supply plus constant exhaust, basically exhausting through the usual code mandated exhaust fans, combine that with supply systems. But the ultimate way to do it, the Cadillac, HRV or ERV balanced system, keep it independent of your HVAC system, primo, beautiful, awesome stuff. So a lot of the time folks say, well, we have exhaust fans, but we also have trickle vents. They work great, don't they? Basically to me, a trickle vent is just adding an engineered hole to outside. And remember that exhaust fan, that's pulling on the entire building shell on all sides. It's going to draw air through that engineered hole at the rate, basically at the ratio of that hole versus the rest of the hole of that shell. So, I actually went, basically the takeaway is that for that to actually be a useful source of outside air, you have to build insanely tight that nobody actually achieves. I actually did a measurement on one of these buildings. They had these trickle vents that they spec'd in. I threw my flow hood over that, where we're drawing 100 CFM through the exhaust fan, 10 CFM is coming through the trickle vent. Yep, that is just a trickle indeed. So that name is accurate at least, but it's not a very good system for delivering outside air. Moving on to exhaust ventilation rates. So there are all the requirements from building codes and Energy Star of having ventilation systems in the bathrooms, in the kitchens. And one of the things that I typically put on my laundry list when I'm investigating these buildings is go ahead and throw on a little exhaust fan meter just to see how much they're flowing. Typically they are doing their rated required amount or even more than that. One thing to remember if you're ever doing this test yourself, a lot of these fans ramp up over a minute. So you're like, this thing isn't on. This thing isn't on. Come back. God damn it. Okay, got my number. So a common problem that I've been seeing is the original mechanical design for these individual units was correct. One bathroom with a constantly running fan to meet code requirements, the other one with an on-off switch just to exhaust odors. Show up there, both of them are wired to be running 24/7, 365. We have 2x the code mandated exhaust rate. Guess what happens when that occurs? Yep, you have more outside air coming into your building. Detour into the ventilation rates. So the old 2010 ASHRAE 62.2, which Joe was a proponent of, 7.5 CFM per occupant plus 0.01 per CFM per square foot. ASHRAE, the 2013 version, bumped that up to 0.03 CFM per square foot. Basically, the square footage added load. What does that add up to? For a 1,000 square foot, 2-bedroom apartment unit, we're talking 33 CFM under the old code to 53 CFM. Not quite a doubling, but a significant increase. Like we said, where's the moisture load coming from? The outside air. And admittedly, I know that a lot of engineers overspecify the airflows just because they are used to the crappy old central systems that are going to be drawing, twice as much as what you need on the top floor and a quarter of what you need on the bottom floor. These systems are incredibly difficult to balance, so they often just say like, yep, turn it up to 2x and we'll actually get something close to what we need. On top of that, the pandemic, pushed for increased ventilation rates, once again, pushing up these types of problems. So, rocketed through all that ventilation stuff. Any questions, comments? Where everybody's hitting the post-lunch low. Oh, yes.
Even with a properly sized pump in your apartment, moisture recovery isn't that great according to the good ERV, right?
The comment was about, is the moisture recovery of the ERV that great?
Every time the interior humidity increases, the recovery efficiency decreases, you're actually making more moisture from it.
Absolutely. There are some people who are under the misimpression that an ERV is a dehumidification device. It is no more a dehumidification device than insulation is a heat generating device. It basically makes the outdoor air suck less. It makes it, kind of closer to what conditions are inside, but it will never be as dry as inside. So completely agreed. Even with a good ERV, you are not dehumidifying. You are still adding heat. You are still adding moisture load. Absolutely true. Just less than if it was raw, untreated air. In back, please. Yeah, Bart's comment was, stack effect and these multifamily ventilation systems that are going up in a big, big tall building. That is their fundamental weakness. If you ever get a chance to chat with Lorne Ricketts from RDH, he did an entire massive study on that problem, basically showing that, stuff doesn't work. Your stack effect is overwhelming your fans when you're going all these stories, unless you're jumping through hoops with, constant airflow regulators, calibrated orifices, all those kinds of things. So that's a fundamental weakness. Yes, please.
As I've been working on more passive house buildings, people have started asking me, but where is the air that the kitchen exhausts coming from? Can you help me answer that?
So the question, where is the kitchen exhaust makeup air coming from? Once again, it's through the hole, ultimately through the holes. Whether it is the shell holes or maybe increased draw through the ERV system, I'm not sure. It all depends on where those all pencil out, right?
Or let me ask the question a different way.
Yeah.
In passive hosts, is it an established problem? Has anyone seen problems with those kitchen exhausts causing airflow issues?
I have personally not, all of these moisture problems that I'm dealing with, these are not passive house. All of them are typically Energy Star or that level. I have not dealt with passive house specific problems, worth a discussion over beer to see what other people's experience has been. Okay. Yes. Oh, James, what's up? What do I think of dehumidifying the supply ventilation air downstream of the ERV? We're going to get to that. Totally agree that is a move in the helpful direction for sure. Okay, another detour, getting off of mechanical systems, putting on my building enclosure, building shell hat for a bit. Like we said, these exhaust-only systems are drawing, the source of that moisture is the outside air, and exhaust-only ventilation is drawing air from the outside through the shell. And basically, these Energy Star buildings, typically they are doing air leakage tests, they're paying attention to things. So, you don't expect giant dumb holes in those projects. And it's kind of interesting to see where those holes end up being. They're often tricky and weird as an example. So this is one case. Here's a section of the building cut through a balcony. You can see the way that there are open web floor trusses where the air conditioning duct is running, both in the roof truss and in the truss between the top floor and the next lower unit. And you can see the plans show and call out closed cell spray foam. Like that should do a decent job of things. What's going on? Why is the condensation so bad on this ductwork? We pop a hole up in there and we can definitely see, yep, they sprayed spray foam like they were supposed to. What's going on? So we go ahead, bring the blower door out in the middle of summer, start pulling negative, and what do we see? It's like, why is there that giant glowing hot line at that wall where the balcony is? Well, we went ahead and started to disassemble things, cut a hole in the ceiling, and you can see that this is all a sequencing problem. Basically, they brought the spray foam guy in, he shot that, but they left a 1-inch gap where the hat channel and the drywall has to go. Basically, it is this nice little line of air leakage that was not sealed while the spray foam guy was there. Basically they had got almost everything right, but not quite. So that's part of the reason why we were seeing condensation so bad on all of that ductwork in that space. Similar kind of situation, that unit where that little red outline is, that is facing the unconditioned stairwell and the unconditioned utility room. And you can see in that infrared shot where we're pulling negative, behind the Sports Illustrated swimsuit issue that the guy hung on the wall, you can see once again we're sucking in hot outside air like crazy through one of those annoying little interfaces that just did not get sealed. Another classic problem I've seen over and over in these things is the rooftop has all of those outdoor condenser units, bang, 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 walking down in rows. The line set and the electrical come up through these dog houses typically. Basically, line set with insulation and comes out through the sides of these things. Great for water control, but if you pop a lot of these open, you can basically look down at the foot-size hole that they carved in the roof sheathing, which is basically the line from inside to outside. I can basically take my tape measure, run it down, and knock on the ceiling of the top floor unit below. It's wide open. So this is what it looks like from below during the winter. You can just see all of that cold air getting sucked in by negative pressure. Basically, it is a big hole to outside. No big surprises here. So, basically whenever I see this condition, the retrofit that I have to do is either shoot it with closed cell from the bottom side, or you're patching in rigid foam and a foam gun just to fill up all of those stupid holes. It's a pain in the butt detail, but hey, it's a hole from inside to outside. We got to do something about it. Oh yeah, and in addition to those unintentional, accidental holes, there are a whole lot of intentional holes that you see problems in. For instance, a lot of these are code mandated to exhaust the kitchen to the outside. So there's actually, it's not a recirculating range hood forehead greaser, which is, as John Straub puts it, recirculating are about as useful as a recirculating toilet. So what ends up happening though? We're pulling the building negative a lot of the time. Oh, that's where the moisture ends up and basically stuff growing on all the food splatter that happened inside the microwave. Believe it or not, your exhaust fan actually does pull from the microwave box. I've measured this, I've checked this myself. Like, hey, the smoke is clearing out after I burn my oatmeal. Doesn't quite show up great in infrared, but definitely you could see the outside air getting pulled through that. In a similar vein, there was, reports, the ownership guys are saying, oh, we're getting condensation inside of the dryer, on the clear window. Yep, exactly the same thing. Pulling that air in, hitting the cool surface of the dryer glass, condensation. So one question that I get is, why the halo of mold around the ceiling registers? The obvious thing is duh, that's where it's cold. And then I said, wait a second, the cold air is the driest air, so that part shouldn't be condensing. But then you think about it again and go yeah, it becomes cold and then all the rest of the humidity comes in, condenses on the cold louvers, condenses on that halo. Of course, that's where the problem is. On top of that, those are once again holes to outside. That's where outside air can get sucked in through an exhaust fan or a poorly sealed ceiling louver to outside, another spot where humid air could be coming in on top of that. Also, another thing we see over and over, semi-related problem is, basically attic air hitting the cold duct boot, condensing, dripping around that. It causes, basically another cause of a halo of mold. Okay, now this is, diving into those questions about mini splits and all that stuff and dehumidification. This is, looking at the mechanical systems. So once again, like I said, cooling is the only dehumidification we typically have here. HVAC is controlled by temperature, not by humidity. We have incidental dehumidification from cooling, and we see a lot of these problems seem to be linked with underperforming HVAC systems. So just talking about some of the diagnostic steps that I've done and the fixes that result. So a page from Andy Ask's book here showing a simplified psychrometric chart. How does cooling actually work? So in order to dry out air, you have to cool it down until it starts to condense, sweat out on the cooling coil. So what does that look like? We first have that horizontal, we first have that horizontal line where we're cooling off that air but not drying it at all. Basically, there's no condensation occurring yet. Then we cool it down to near the temperature. Basically, we flow it over those cold coils. Moisture starts to form on those cold coils. We're starting to dehumidify. And you can see that basically if things are operating well, our delivery air will probably be 90-95% humidity, something in that range. Basically, we've cooled it down to as much as we can, wrung as much moisture out of it that we can. Ultimately, if we want to hit those targets of 60% humidity or so, we have to supply air drier than that. So basically, the takeaway is supplying air at 50 degrees Fahrenheit typically is 50 to 55. That's the target we need to be shooting for. Otherwise, we are not actually dehumidifying enough to hit those target levels. So one of the things that I do all the time when I'm doing these measurements, just measure what's called the split across the air handler. Basically, take my step bit out, drill a hole in the supply, drill a hole in the return, take my 2 temperature and humidity probes, shove them in, take a measurement of what is the cooling unit doing. And I can get a measurement of what the temperature difference and what the dew point difference is that's running across this unit. The takeaway is if I'm hitting 18 to 20 degrees Fahrenheit, we're probably, the mechanical system is probably not the fundamental problem. And that works out once again to that math of the 50 degree, 55 degree supply air. We want to get 70 degrees minus 20 degree split gets us that 50 degree dry air that we're trying to look for. I'm sometimes dealing, a lot of these cases, the air is blowing out of the unit at 60, 65 degrees, a much smaller temperature difference. Basically that means that system can never actually get to 50% humidity inside. And I've had some, guys argue with me saying like, oh, no, it's gonna keep on running and run more and it'll wring out the moisture. That's like saying, I can make a room dark blue by taking light blue paint and painting it over and over, and I'll eventually get from light blue to dark blue. No, it doesn't work that way. So this is just like a table from one of these investigations. You can see that units number 1 and 2 were hitting a pretty decent 18 degree split. Those ones are the ones that are working fine. The other ones, lousy kind of 7 to 12 degree splits. Not nearly as good. Also at the same time, I measured the difference in dew point, and you can also see that the ones that are working better have a bigger dew point split. The ones that are working worse have a lousy dew point split. No big no big surprises here. A good temperature split is all you really need to know about. So the culprits that can be going on here are airflow problems or refrigerant charge problems. Before we dive into those topics, let's talk about a PTAC unit. So all of us have been in hotel rooms looking at these units. They're noisy, clanky, and annoying, but the ones that I've measured actually do give you a decent split in what I've seen. 18 to 20 degrees when they're running, they actually do a decent job of dehumidifying. That's when they're actually running in cooling mode. The problem is when the cooling system turns off, and the fan is still running, you actually end up seeing, it's sending cool, clammy air. It is actually evaporating moisture off of that cooling coil and sending it back to the room. You have an incidental humidification system in the summer. The PTAC is adding moisture back into your room air. Unfortunately, most of these PTAC systems that I've seen, the factory default is, continuous fan. Some of them have switches, but most of them don't. So, and it's super annoying to dig into the manual to find that. So we're going to talk a little bit about the airflow over the coil. So this is one of the key points that I'm dealing with on a lot of these investigations. The layman term that I always use is you want to run the air low and slow over the coil. Basically, give that air a whole lot of dwell time to sit over the cold coil, condense, wring out that moisture until it keeps on moving. In more technical terms, this is referred to the metric of CFM per ton. Cubic feet per minute of airflow per ton of cooling. Basically, ratio of how much airflow to how much cooling is being pushed into that coil. So the standard is 400 CFM per ton. So for instance, an 2-ton air conditioner system, 800 CFM of air. No big surprises there. So there are cases where you bump up the airflow if you are in places where human beings should not live, like Phoenix and Las Vegas, where humidity removal does not matter. You can bump up the airflow to 450 CFM per ton, better efficiency, lower humidity removal, but in Vegas, who cares? You're just trying to survive. In wet climates, what you want to do is, like I said, low and slow, dial back the airflow and drop it to 325, 350 CFM per ton. You are increasing your humidity removal, but losing efficiency. But unfortunately, removing moisture just costs energy, full stop. There's just the nature of the beast. Just an interesting little data point. The home innovation guys, NAHB Research, did a study looking on, playing with modern air conditioner systems. They dialed it all the way back to 200 45 CFM per ton. No problems with freeze up. I think that might have to do with modern, bigger coils, that kind of thing. But basically there's more room, possibly more room to get even more dehumidification out there. So how do we actually set the airflow and how does that work? This involves, I know this is shocking, opening the manual and looking at what the instructions actually say. So, there are cases where, getting out your reading glasses and looking what the dip switches, those tiny little switches on the control board need to do. Basically, you're looking at like up, up, down, up, and that gets you, and then you realize I've been doing it on the wrong bank. God damn it. Or, connecting up which the red wire goes to this port, or, wire up the pink thing to the yellow thing, or the purple wire, all those kind of things. Unfortunately, a lot of these problem cases that I'm seeing is the installers just take the box, drop it in, and it's left at literally the factory default. Why is this a problem? Well, a lot of these cases I'm seeing, default is 2 tons, 800 CFM of airflow, which is great for a 2-ton system, except they're putting a 1.5 ton unit on the roof. So basically, they have turned it to the do not dehumidify at all setting, accidentally. There are great HVAC techs out there. Brian Orr, if you're in the audience, you are making more of them. They are not the ones being hired to drop boxes into multifamily buildings, I'm sorry. Sometimes I get the pushback of like, oh my God, we have condensation on this ductwork. You can't turn the airflow down more. We're going to have even colder ducts and we're going to condense even worse. Remember, this is an inside ductwork problem. We're trying to control interior humidity. Basically, that ductwork is inside and that's where it's sweating, between floors. Basically, I say, let's just try a little math here. Here's the basic formula. The amount of BTUs per hour is equal to a constant times the temperature difference times the airflow. The amount of cooling provided before and after is going to be the same. Do a little bit of high school algebra, and you can figure out that going from 400 to 350 CFM per ton, basically dialing in good dehumidification, that means 2 degrees if there's no difference in sensible heat ratio, which there definitely will be. That's what we're trying to do here. So 2 degrees is not going to make a difference on a condensation problem like we're seeing inside there. Something else is going on. And basically I have to pull out sarcastic Willy Wonka saying like, so we need to solve the humidity problem, but you're telling me we can't actually improve dehumidification? Swell, thanks. Last piece of this is the refrigerant charge. So basically, the refrigerant, the working fluid inside the hermetically sealed system, can have a large impact on the coil temperature, its moisture removal, all of those factors. Too much or too little can cause problems. One of the issues that I suspect is going on is a lot of units are pre-charged for 15 feet of line set, typical for residential, but then you have a multifamily building that's 4 stories tall. You're probably losing that 15 feet just getting from outside to the corridor, not to mention that vertical run. So unless they're actually weighing in charge correctly, accounting for that line set, we're probably running at a deficit. So questions about ductless heat pumps. They come in smaller sizes. Yep, so down to 1 ton, that's definitely a better match to the type of units we're dealing with here. They're modulating, that's always in the helpful direction, but I have seen plenty of cases still with humidity control issues. During peak load, sure, you'll have a cold coil, but remember that outdoor unit is ramping up and down, modulating, and the valve on the coil inside is also ramping up and down. So when you're in part load conditions, you have a warm coil, less dehumidification, back to square one. I assume a lot of you who have mini splits have played with dry mode or whatever your brand calls it. I've personally found it underwhelming. All it does, when I've seen it is like, yep, it makes the space colder, and that's about it. Oh yeah, Mark says like, oh, it also has a bonus of using more energy. Andy.
Have you looked at what running these modern heat pumps at the sensible ratio?
Have I looked at what the part load numbers are for sensible heat ratio, is what Andy's asking. So I've not had a chance to study that. I've not had an opportunity.
Not published.
Often not published. Was that Steve back there? Yeah, so somebody has a good performance map, figuring out those numbers, that would be very useful industry to get out to the world. Mini splits and VRFs. For those not familiar, instead of one box on the roof, one box inside, that's one big box on the roof connected to many boxes inside. And they don't modulate the same way as mini split heat pumps. The problem is you take the big box, dial it down to 30%, it's probably more flow than what an individual unit in an apartment is handling. So there's a lot of mismatch problems along those lines. I've not done many of those jobs, so somebody else can probably speak to that better than I can. But just kind of equipment we're talking about. Just another example, this is still true with the air handler style, the ducted units. Basically, the folks who investigated this before me did the same kind of split measurement and said like, yep, we're getting 9 degrees across the coil if this thing isn't dehumidifying. Absolutely correct. What I did do while I was there is I actually forced it into high mode. I ran it at, for heating for half an hour, walked in and investigated another, unit, bumped it to 80, 85 degrees, slammed it down to cooling at 65 degrees, and then I got 20 degrees across the coil. Yeah, exactly, using reheat, non-synchronous reheat, right, Bruce? Once again, basically you've dialed back the rooftop unit, you've dialed back the inside coil, you're getting warm air pushed out of that unit. So this is really frustrating to me because literally all the parts we need for good dehumidification are in these boxes. And the product rep is telling me like, nope, our controls don't work that way. You can't actually force it to run in high mode. Like, frickin' seriously? You're causing these you realize that you're biting yourself in the butt by causing these type of problems, and that's one of the issues you'll see. Once again, dry mode, I measured it on that system, underwhelming. Last piece of this is, when occupants are playing with the mechanical systems, that can also hurt what your interior humidity looks like turning your cooling on and off, opening up windows, letting outside moisture in, that can be non-helpful. Super cold set points results in super cold ducts, making some of those condensation problems worse, as well as grandma doesn't like it that cold. Super warm set points means the air conditioner never runs and you don't get any dehumidification. And lastly, fan on versus fan auto. Like we said, this is a rehumidification system to basically take moisture that you spent money to get out of the air and put it back into your apartment. And lastly, those ventilation fans left on 24/7 is just going to give you more and more outside air that you're dealing with. So like we said, putting this all together, better enclosures, better shells means less cooling load and less air conditioner runtime and less incidental dehumidification. Shoulder seasons when the sun is not blasting on every single surface are often going to make things worse. And oversized cooling equipment by factor of 2 or 3, just by the nature of these loads, is going to result in poor dehumidification. 2-stage, multi-stage helps, but it's typically not enough. High efficiency equipment, worse dehumidification, and adding supplemental dehumidification is going to probably be more and more necessary in the future. So, any questions before I jump into dehumidification? Andy?
So when I get my E-gauge out and I'm looking at how my heat pump is running and it's bouncing up and down between full speed and nothing, I'm getting cranky because it's not modulating. But maybe it's doing a better job dehumidifying.
Yeah, Andy's comment was, mini split heat pumps are supposed to kind of ramp up and down and modulate, but if they're oversized, you'll go basically run and then drop to 0, run, drop to 0. But his point is like, maybe it's a dehumidifying slightly better. It's like, yeah, that's a fair point. It might be. I'd measure it just to check, but I'm curious myself. Yeah. Yeah. Oh, sorry, Kimberly. Hey.
Hi. Oh, that's loud. I'll stand back. So before we move on to the next section,
Yeah.
just two things. One is going a good ways back to where you, I'd like to add a qualifier to where you mentioned that mechanical installing contractors generally just drop in the default and let it run. Now, out of that, I've probably looked at many hundreds of plan sets by now from mechanical engineers, and I have yet to see the design call for a lower CFM. So
Entirely
if
fair.
we expect for the installing contractors to adjust those dip switches, it should be on the plan sets.
Entirely fair, yes.
Okay.
True.
The other comment is about an industry-wide problem we have with this year 2 specifications, which apply to all of the climate zones that you're talking about, 2A, 3A, and 4A, but they also apply to all of our dry south climate zones. So what drives mechanical system sales and product development are actually rebates. I don't know if that's obvious to everybody. Those rebates are attached to those efficiency requirements that are established for the entire South region. So this is a problem I think we can all work on, which is to have climate-specific efficiency standards.
Yeah.
Okay, that's number 2. And 3, I'll be real quick with this one. This is a little bit about why dry mode hasn't worked. In the past, first of all, Japanese people, our engineers, I just had a meeting with one last week who was asking me why we need our spaces so dry. They're comfortable at 80 degrees dry bulb and 60% RH. So this is actually a major problem.
Hey, I'm Japanese and I'm not comfortable in it.
Sorry, let me qualify that. I think you've acclimated to the U.S. Sensitivities. But this is genuinely an issue. Also, those dry modes have not functioned using humidistat until very recently. So we're working on that, and we're working on the partial load SHF data.
Awesome.
That's all.
Thanks, Kimberly. Steve, what do you got?
Just a comment. There's a very simple way you can often double the dehumidification of a single-speed system, and that is by changing the temperature swing, AKA deadband, AKA temperature differential. Several thermostats default to like half a degree. If you change it to a degree, you probably won't
More
notice a
runtime?
comfort difference, and your cycles will be twice as long.
Nice, very nice. Sorry.
I have a deadband of 2.
Yeah, same comment on deadband like that? Nice. Oh. Kirk, what do you got?
Oh, just in terms of the loads, I guess I'd build on what you're saying. It's not that there's just less cooling load, there's also the sensible heat ratio of the load has gone down too.
Absolutely.
So that's another
both the cooling
confounding
loads
factor.
and as a result, the SHR. Yeah, I think I'll power through dehumidification and just get to the case studies here. So, cheap and easy way, if they're running like an air handler in a louvered closet, just drop in a standalone dehumidifier. That's not a bad solution, but too many of these problem cases that I'm dealing with just don't have that kind of space to work with. Inside the wall, recessed mounted systems, talk to the Thermistor folks. They make a beautiful unit. That is a great solution, although you will get a lot of pushback on cost, given that these are about $1,000 compared to like a $200 Sears commodity dehumidifier. Using some beautiful ducted dehumidifiers, that is the primo solution, but in a cheap multifamily building, you're very unlikely to get owner traction on doing that. The one exception that I've dealt with is, they're doing basically a ducted system to the corridor to condition those spaces. And in that case, you can sometimes convince them, put a honkin' big dehumidifier in your hallway mechanical closet, dry the crap out of the hallway air, and maybe that'll help you the rest of your units. And also, like James said, dehumidifying your outside supply air. Yes, sir, please.
So I think the answer, seriously, and you're going to take this probably sarcastically, is we go back to 10 SEER systems because the energy efficiency is coming at a cost. We're raising up coil temperatures to decreased compression ratios, costing basically the dehumidification. We could go just the opposite direction and realize that humidity has cost. Now, you put a humidifier on, you just doubled your maintenance cost. They're very good at removing humidity, but they're also use a ton of energy. So there's no savings here. There's no free lunch.
Yep, that's an entirely fair point. I've never done the math on what that adds up to, but I would not be surprised if what you're saying is absolutely dead to nuts right.
The other thing is that when you drop the airflow below 275 CFM per ton, the latent load holds up the pressure, the suction pressure on the machine. Because the energy doesn't care how it gets through the coil, whether it's latent energy or sensible energy. Energy goes through, creates pressure in the refrigerant, holds up the coil temperature.
Thank you.
Yep.
And then, basically the big systems that might go on the rooftop in one of these cases, makeup air or dedicated outdoor air systems. The whole concept of that is preconditioning the ventilation supply air and basically preheating, pre-cooling, pre-dehumidifying your ventilation air before you're introducing it to your building. James was talking about that, and that's the type of beautiful systems that he's putting on a lot of our fancy projects together. And it separates out the heating and cooling loads in the individual units versus how do you precondition that outside air problem. And you have to supply your supply ventilation drier than the target. If you're pouring pigment into the paint can, it has to be darker than your target color. Same concept. But this type of equipment costs absolutely, and this is not this is high-end, fancy rooftop crane kind of stuff. This is not stuff that a typical residential tech is ever dealing with. So estimating humidity loads, this is where I was kind of winging when they were saying, how much dehumidification do we actually need in our building? So, I can definitely kind of eyeball what the dew point is outside during that period, what's our airflow, and then, say, what maybe half of that load is dealt by the cooling system, and basically calculate how many dehumidifiers are needed. This is a ballpark guess more than anything else. But the simplified way that I often pitch it to owners is that, a 75 CFM exhaust fan is about equivalent to what a standalone dehumidifier is going to remove in terms of pints per day. If we assume that your air conditioner is maybe picking up half of that load, okay, 75 CFM is half of a dehumidifier-ish. But that's, that is the impact of taking untreated outside air, bringing it inside. Those are the costs involved. Any discussion before we jump to finish off with some quick case studies? Padian.
Can you tell me how much it costs to run that dehumidifier at 20 cents a kilowatt hour?
I do not have a number, but it definitely oh, somebody has an answer?
Isn't it more than an Energy Star refrigerator?
I would believe that.
I can tell you exactly what that one is, because I have it in my basement at 13.5 cents. It costs me about $8 a month.
$8 a month at 13 cents per kilowatt hour.
But how much is it dehumidified? Yeah, significant.
Nikki.
Residential Energy Dynamics has an energy calculator on their website, and I use that in the watts of a dehumidifier, how often you think you're going to run it for your kilowatt, and it'll give you the cost of what it is to run that dehumidifier.
Yeah, Nikki was just saying that Residential Energy Dynamics has a calculator where you can just punch in those numbers with the efficiency, which would tend to make a decent selection to a very nice high-end dehumidifier, right? Padian, finishing that off?
I think you're a salesman for window air conditioners.
That's a fair point. So, just, a little, here are little snippets of, what did I see out in the field and what resulted. So, this was, ugly block house, 1950s, Savannah, Georgia, public housing. Uninsulated block walls, and then they did a renewal program where they just took all the crappy aluminum frame single glazed windows out, dropped in nice, lowy, windows that actually open smoothly and don't fall down. And then they started getting, the air conditioning system was actually replaced reasonably recently before then, no change. And then what did they end up getting reports of? This is looking at the ceiling of the first floor unit underneath the exposed duct. I don't know if you can quite make out all of that black staining on the ceiling above the duct where basically that cold is radiating out. Basically, they developed cold surfaces and things went south from there. Also growing inside the HVAC boxes on other parts of the ceiling. This is just, literally the one change was going from crappy single glazed reheat windows to modern double glazed, and that problem ended up resulting. Kind of surprising it was that immediate. Uncontrolled central fan integrated ventilation. So this is a multi-story, multi-family building. You can see that gooseneck that runs from the roof down to the HVAC closets, and each of them has a little duct running from that big trunk to every return in the unit. And it's a one of those semi-balanced system, central fan plus an exhaust fan. Yeah, it's kind of balanced. The problem is that there's no motorized damper on those outside air ducts. So if I was going to design a system that, basically when it's hottest and I want the least amount of air, let's put more outside air in. That's basically what they built there. During the summertime high run times, more outside air. In case that looks like a motorized damper, that's just a fire smoke damper in that picture. And on top of that, the building was depressurized. So basically the outside air was getting sucked all the way through from the rooftop through the return side. An example right around here in the Boston area, they built with what's pretty modern construction, zip wall sheathing, taped seams, spray foam, unvented roof, good stuff. And all of the guest rooms in this hotel were, constant exhaust fan operation, no makeup air system, and you put a manometer down through the front door. The whole building's running 10 pascals negative. They turn on the kitchen exhaust fan and it jumps to 15 pascals. It was bad enough that the fireplace in the lobby no longer drafted. Basically, they built a fire and it just sucked right down until they put an Enervex fan up on the top of the chimney. VRF system, the same building, they were running 70% humidity in the summer. You could actually see some spectacular movement in the trim to basically how much the humidity was cycling in the building. There was a decent split at the head, but once again, constant fan runtime, rehumidifying, evaporating that air off the coil, sending that moisture right back in. And I have to say, you have to dig a lot to find the settings where it says turn off fan cycling in these units. Mark, you probably fought that fight too. How much exhaust flow? So this is another multifamily building, Philadelphia. Once again, I measured across the window, 12 pascals. It's kind of weird where you open the window and oh, that's a stiff breeze coming in today. Go to the other side of the building, that's a stiff breeze coming. Wait a second, that's not right. Basically, and the trees aren't moving. So basically, I went and dug into the test and balance report that they sent me. And so the central core of the building has gigantic rooftop units that are both supplying and returning air to it. And added up all the test and balance numbers, supply reasonably balanced to the exhaust. That's a little bit of excess exhaust, but nothing too crazy. Then you add on all of those individual residential units with 100 CFM of exhaust each, and that's what it looks like. That's where the problem is coming from. About twice as much exhaust as, that's where the minus 12 pascals is coming from. So basically, engineers were jumping through hoops, how much can we turn down the exhaust systems? Demand control ventilation in our conference rooms, turning an exhaust riser into a supply riser, dropping in new equipment on the roof. But you're old enough to know the movie Jaws, right? We're gonna need a bigger makeup air unit. Okay, so the takeaway from all of this is, folks are blaming new buildings, Energy Star, efficient construction. That's not fundamentally the problem. It's untreated outside air that's not being dehumidified and drawn in, as well as uncontrolled air leakage. Equipment that is not dehumidifying well, whether it's the sizing, the settings, other issues, refrigerant charge, CFM per ton setup, occupant behavior. There are plenty of ways where stuff like that can make things go wrong. And often, a lot of, when I'm being called to these buildings, it's a perfect storm of like, oh yeah, you did all exhaust, and you had a terrible install, and there's refrigerant charge problems, or there's additional exhausts that have been specified. All of those things add up, tip things over the edge. And the thing is, we used to get away with them, these kind of marginal problems in many situations, but once again, you add these all up together, and yep, it's enough to tip things over the edge, at least based on the calls that I've been getting. So like I said, we should keep on building good buildings. Pay attention to airflow rates. Remember that exhaust fan equals dehumidifier. That's what you're buying. Balanced ventilation is best. Maximizing your dehumidification with your settings, and your air leaks can still bite you. Pre-planning dehumidifier connections, not a bad idea if you have the opportunity. Basically a plug and a drain in the mechanical closet, not a bad thing. And if the problem occurs, go through the list that we talked through before, field measurements of splits, and then if that doesn't work, dehumidification. Okay, back to you, Joe.
All right, we have room for 2 questions before we have brownies.
I've got 2 things I wanted to mention. Maybe questions, maybe not questions. Personal experience in my very humid climate, if you get below 300 CFM per ton, you're real close to a freeze-up issue. So if you start, it may work perfect until your air filter gets dirty or something like that. So just be warned. Number 2, also in my humid climate, if we have a 20-degree split across a cooling coil, we probably already have a dirty coil, because we tend to run 14 to maximum of 18, or we've got an airflow problem.
But Ken, just to finish that off, 350 CFM per ton, not a bad spec for you?
Oh, real good.
Okay.
Real good. And we try to push it lower when we can here.
I have a question here. For a dehumidification system off of your HRV supply, did you speak about that at all? Like a solution for that? And can you speak?
Yeah, so putting a dehumidifier connecting through the HRV or ERV supply duct. I did not actually talk about that. James asked, does that make sense? And that sounds pretty reasonable to me. Where it belongs in the chain, upstream, downstream, I think smarter people than me need to figure that out. Talk to David Trelevin, he's probably in the audience somewhere. Okay, there you go, talk to him.
Thank you.
Kohta, your window replacement job showed one of the ultimate laws of unintended consequences. Every utility program in the country is going to have this same problem, because they replace the air conditioner with like size. And then they think, oh, these people have saved a little money, so they're going to replace their windows or insulate or air seal or do these other things, when they should have done it exactly the other way. Reduce the load first and then size properly. So many utility programs are seeing these moisture problems because they're dropping in a 4-ton unit where there was a 4-ton unit and they really only needed a 2-ton unit.
Oh yeah.
Henri?
Kohta. My understanding was that if you added a dehumidifier, some of the cooling load was reduced because you gained comfort at a higher temperature in the unit, so to speak.
Yeah, that's perfectly plausible to me. Just to kick out another benefit, though, of a dehumidifier is it's dumping insane amounts of heat into your house, causing more air conditioner. Basically, it's it's giving you an extra bonus of air conditioner runtime.
All right, we're done.